Hello everybody and welcome back to our weekly seminars at BrIAS after a small interruption of a few weeks for the well-deserved vacation. So we are back with a very nice program in May, which will consist of several very interesting seminars and various events, among which I want to remind you the one on the 19th on critical underwater infrastructure and the conference on batteries that will be in the same week. But anyway, we can start today with two very interesting seminars. The first will be from Professor Paolo Falcone from the University of Modena and Reggio Emilia and Chalmers University, who will introduce us something about cautious by design motion planning, the role of prediction. So Professor Falcone is an expert in the usage of MPC for various sort of mobile robotics, in particular for vehicles of various sorts. So I will not saying too much more blah blah blah. I'm very happy to introduce him and to leave him the stage.
Thanks, Manuel, for the introduction. Thanks for being here, and thanks for the thanks for the invitation to BrIAS. It's been very enjoyable so far. Okay, today I'll talk about the results from some research activities in collaboration with PhD postdocs at Chalmers and Unimore, but also in collaboration with companies like Zenseact, that's a kind of spin-off company of Volvo Cars, and based in Gothenburg, and Ericsson. Okay, so let's move on. Let's first introduce what motion planning is about. It's in an autonomous driving system, you have a stack, okay, where you have different modules in charge of perception, like context awareness, and a part of this stack are the route planner that you see over there, and path planner, which is what we are going to talk about in this seminar. So the route planner is what you have in Google Maps, in while ago TomTom or Waze or whatsoever, right? So you type in origin, destination, and you get a route, right? So a sequence of points you should follow to get from point A to point B, origin to destination. And that's basically the green line that you see over here. It's, you don't get any route which accounts for what your vehicle can do, right? So your vehicle might be a car, a bicycle, or can be an articulated truck, right? So a combination of long vehicles, but the green line doesn't know that. So that's why you as a driver, while following the green line, you actually plan in advance something like the red line, which is our path, right? You, from the red line, you extract some point which you try to follow, that account also for what your vehicle is. So if your vehicle is a bike, probably you will follow the green line, right? But if your vehicle is a bus, that would be a tough job. So that's why you have, in an autonomous driving stack, you have a module called the Path Planner. That does exactly the job we do every day while driving our vehicle. Okay, clearly we as a driver plan our path subject to a number of rules or constraints. So clearly we plan a path and we follow that path subject to vehicle speed, right? So speed limitation, like the one that you see over here. Clearly you don't plan anything which your car cannot do. So as a driver, we also plan our path subject to what the limitations of the vehicle are. Clearly, you want to avoid accidents. So if, while planning the path of your vehicle, you see a pedestrian or a static obstacle, well, you will make sure that you avoid any collision with any obstacles. Furthermore, you have limitations coming from the vehicle, right? So here we have a steering actuator. Well, a steering actuator is basically essentially an electric motor, and you can't steer as fast as you want. So while planning your path, you should also account for limitation imposed by the physics of your vehicle. Same holds true for engine, braking, or whatever your actuators could be in the vehicles. So to solve this problem, to solve the path planning problem that as I just stated it, in our community we offer a resort to a technique which is called the model predictive control. So the path, so the sequence of points which we plan to follow are the results of an optimization problem. So in this optimization problem, what we try to do is to optimize the future behavior of the vehicle with respect to a number of a future sequence of control inputs, steering command, acceleration commands, braking commands, and so on. So what we do is to have a plan, have a trajectory from the current time up to a future time instance. We just use the first portion of this plan and we throw away the rest. We wait some time. We collect new measurements about the environment, about the state of the vehicle, its velocity, its position, and then we redo the same job over and over again. So this technique is called receding horizon or model predictive control. It's the same terminology. It's two different terminology for the same scheme. So let's try to write in math what we have just said. In our case, what we are going to do is to try to minimize every time instant a cost function. Such a cost could express the willingness of having a red line as close as possible to the green line, right? So please find a path which follows the desired route such that I can go from origin to the destination. But then, as we said, our path must also be subject to the limitation of our vehicle, right? So we should account over here somehow whether our vehicle is a bicycle, a car, a motorcycle, or a truck. And then, as we said, we should also constrain the generation of our path to the limitation of the vehicle, steering limitation, steering rate limitation, and so on. And here comes something painful, a painful ingredient in this recipe, which is a number of constraints that model the collision avoidance against surrounding objects, other vehicles, pedestrians, bicycles, trash bin, parking car, everything that we would like to avoid a collision with. So here is some additional constraints that I'll come back on later on in the presentation. So the way these algorithms work is that the vehicle at the current time instant, so over here, plans the path such that it will slowly approach this, progressively approach this path over here, which is the green path we had before. So this is the future path, okay, that is planned to be followed. But at the next time instant, we redo the same job over and over again. So it looks like a scheme that perfectly fits the path planning framework, a path planning problem that we have just stated. But there are several issues to be accounted for. First of all, this is an optimization problem that we need to solve in real time. So what does it mean? It means that every 50, 20 milliseconds, we need to pack such a problem, give it to a software, a solver, optimization solver, and hopefully get the solution in time, okay, before the 50 milliseconds. But there are a few more issues. One is the stability issues. So how to make sure that the path we get is something which nicely and smoothly approaches the planned route. So we don't want to have something, that is oscillating or eventually deviating indefinitely from the planned route. So that's called stability issues. And there are results which guarantee such that you can eventually stabilize around the green line. So there are results requiring that you generate this green line such that this satisfies this system dynamics. It's a strong requirement That's why in literature you find more recent results from us, but also a little bit earlier, allowing you to also feed this green line over here, which is not satisfying these constraints, and still have a stability guarantee. So, but what we focus on mostly in our work is feasibility issues. What does it mean? What is the feasibility issues? Well, what we want to make sure of is that we never plan a path such that a crash, for instance, an accident becomes unavoidable in the future. So we want to make sure that we always plan a path such that we can still do something in case, for instance, vehicles pop up, pedestrians suddenly cross the road, and so on, to some extent at least. There are results which allow you to make sure that this is the case, and in particular, you can design such terminal constraints, that is constraining the state at the end of the horizon, the position of the vehicle, the velocity of the vehicle at the end of the horizon. For instance, if you are planning to approach the wall, you may impose that the velocity in this position is 0, in such a way that you avoid smashing into the wall. That's just an example. What's the problem with these standard results that you find in the literature? Well, to cook such a set, to calculate such a set, you need to know the system dynamics. So this function f, no problem. Most of the time you have it. And it's fairly accurate. It's a model of the car, a mathematical model of the vehicle. You also need to know this set of constraints, no problem. Most of the time you know what the braking, steering limitations are to I would say, fairly accurate extent. But what you don't know is this constraint. Well, this constraint, once more, model collision avoidance, impose collision avoidance against obstacle that when you code your controller, well, they are not there. Nobody is going to tell you that in 50 meters you will have a pedestrian crossing the wall. So that's the problem with these standard results in control theory. So that's what we have been contributing with. And an example of how these constraints, unknown constraints, so these collision avoidance constraints could be modeled, are given now. So, for example, you can mathematically model the motion of the vehicle with this set of equations without going into the details. So what this model describes is the evolution of the lateral deviation from a path, for instance, from the green path that you have seen before, the orientation error with respect to this path. Here we can model the steering dynamics by using a variable, which is the steering angle, how much we are turning the wheel actually at the road. And these are the actuator dynamics. This is the longitudinal vehicle velocity, so how fast we are going. And this is the acceleration, the vehicle acceleration. Over here we have the commands to the vehicle, which is the gas pedal and the steering angle. That's it. So why am I showing this mathematical model? Because standard constraints on the vehicle motion are imposed by imposing constraints on this variable, these state variables and input variables over here. For instance, here I may want to constrain the lateral deviation of the vehicle from the green line. Why? Because on the right side it could be a sidewalk with a cycling path. On the left, well, it could be probably the other lane, right? So I don't want to have accident. Stay in the lane. That's basically what this means. So over here, I have other constraints, for instance, reflecting limitation from the steering actuators, the engine, and the brakes, the braking capability, and so on. Let's talk about these collision avoidance constraints, how we can build such a mathematical function, such an inequality. Well, in this, over here, this is just an example. You can do it in many ways. This is only one of the different possible ways you can write this inequality. So this could be a collision avoidance constraint saying, for instance, make sure that the minimum distance, so here is written as a maximization, but it could be like as the minimum distance from a pedestrian is larger than something. So this means don't get closer to an obstacle more than, I don't know, or less than 3 meters or whatever. So this function clearly is function of the vehicle state and input. So it's function of the vehicle position and velocity, but it's also function of some additional variable that describes where the obstacle is. So this W, for instance, could be the relative position of the pedestrian, the other car, with respect to the vehicle. And clearly it's uncertain, right? So it's difficult to model what a human will do, whether it's a driver or a pedestrian. So the approach, for instance, we have followed is to model this, the motion of the obstacle we want to avoid as a dynamical system driven by a bounded noise. In the most general setting, you may also want to model the interaction of the pedestrian with the vehicle, right? So that's why over here we have also the vehicle states and control inputs. So an example that we have used in one of our publications is to model the pedestrian as an agent that follows this line on a sidewalk or along a crosswalk. So in this case, just to speed up, which is just a technicality, what happened is that we can describe a set of pedestrian's position at the next time instant, in 2 time instant, in 3 time instants, over all the prediction horizon. So basically, in our optimization-based motion planning, what we are going to have is a set of pedestrians' obstacle positions where we are not supposed to be over the prediction horizon. So that's the way you plan actually your path. So to make everything working, we need some assumption, as usual. Well, the first assumption we use is that there exists a safe set. Let's make some example. You are on the city center. A safe set could be, for instance, pulling over the car on the right. Clearly, such a set wouldn't work in the middle of an intersection, right? I mean, if you suddenly stop in the middle of an intersection, most likely you're going to end up in an accident. In a highway, that could be the same, right? So we assume that such a set exists. Clearly, that may not be the case. Well, in those cases, this approach doesn't work. There is a second assumption, which might be a little bit strong, but makes a lot of sense in practice. This is called the consistency assumption. What does it mean? So let's make an example of consistent prediction. So at time k, I make a prediction of where a pedestrian, this vehicle makes a prediction of where the pedestrian could be at time k plus 1, k plus 2, k plus 3, okay? So the red set that you see here describes the uncertainty, okay? Clearly, I know where the pedestrian will be in probability. Okay, so I make my decisions. I evolve of one more step. I'm now at time instant k plus 1. Still, I have to predict where the pedestrian is going to be at time k plus 2, k plus 3, k plus n. So this time I make my prediction. And this green set is, again, the uncertainty about this prediction at time k plus 1. And same meaning for this green set, same meaning for this green set. Consistent prediction is such that the uncertainty in at time k plus 1 is less than the uncertainty at time k. And that makes sense, right? So I'm predicting whether how the weather is going to be tomorrow. The closer I get to tomorrow, the less my uncertainty is. This is an example instead of inconsistent prediction. So you see that the green set is a little bit larger than the red set, okay? Clearly, this assumption might be broken. Think of I'm turning, okay? And suddenly I get my sun in the cameras of my vehicle. So I lose a sensor, I lose my camera, and then the uncertainty on my prediction is going to grow. That's unavoidable. Or I have a sensor failure, or suddenly it's foggy or snowy. So there are many cases where such assumption could be broken. Okay, so let's see how all this works. This is some simulation. We are simulating a vehicle, negotiating this intersection with a pedestrian. So here we have a pedestrian, we have a crosswalk, and here we have our vehicle. So we formulate our motion planning problem as described before, completely disregarding whether the predictions we made are consistent or not. Let's see what happens. So what you see here is that I guess you can see over here, here you have two different colors. This is the sensor, the onboard sensor field. So we can detect the pedestrian over here. We cannot detect the pedestrian over here. So what happened is that, well, here there is no constraints, right? So we can go freely. But then suddenly a pedestrian appears here, and we have this surprise, right? So suddenly we are not allowed to get in that set anymore. Well, that's basically a case where the consistency assumption is broken. As a consequence, the vehicle doesn't manage to stop in time, and there is a collision. So you can see here from the lateral error, the orientation error, and the steering that the planner is also trying to do something desperate, right? Braking, but also steering. But yeah, the collision is unavoidable. So you see that here is the acceleration. This blue line is saying that the vehicle is making full stop, an emergency braking maneuver. No way. We have killed the pedestrian. Okay, but then the results we just gave says that if our predictions are consistent, then we can avoid the accident. How can we make our prediction consistent? We have seen that just because of the limited sensor field of view, well, our predictions are not consistent. So what we do then is something which, as a driver, we do all the time. So here we have a crosswalk. We can see those pedestrians. But here, there might be a pedestrian that is there. We don't see it, but then suddenly starts walking. So what we do here is to drop some ghost pedestrian. And all the time, we assume that this ghost pedestrian is going to cross. Clearly, that may never happen, and we might be overly conservative, but that's what we do, right? I mean, if we see a parked bus and then a crosswalk, we are cautious, a little bit more cautious, right? We slow down. Why? Because someone may start crossing, but that's a kind of natural behavior. Let's see how it works. So over here, you see that we have a kind of ghost pedestrian, but we are slowing down because we propagate this set. So in this set, we are not allowed to be. This might not be the case at all, never. So the pedestrian may not show up over there, but actually, suddenly a pedestrian shows up. Okay? So this is the predicted position. And you see here, consistency applies, consistency holds. So in this case, we have all the time to slow down and brake in time to avoid a collision. Okay, so again, we are introducing a little bit of cautiousness in our planner to make sure that we can handle unexpected situations. So we have done tests with multiple pedestrians. So we have a pedestrian over here and a pedestrian over here. We can handle this type of situations. So those are this is a replay of an experiment that we have done. So in this case, we apply the same technique to avoid the collision with this pedestrian and with this pedestrian. So over here, you see the lateral error, so the deviation from the green line, the orientation error, the steering angle that we command, and this is the velocity. So we speed up, then we slow down to make our left turn. And at some point, we stop to let this pedestrian cross. But then we speed up again, and we see that no collision is possible with this pedestrian, and then we go. That's what you will see in the following animation, and then with the experiments. So here, it's an important information. how expensive is in terms of computational complexity our approach? Well, this plot shows that the maximum time it takes to solve our optimization problem was 40 milliseconds, well below the 50, well, slightly below actually, the 50 milliseconds, which is typical for this type of application. So this is a replay of experimental data. Now you see basically the animation corresponding to the previous simulation results. So, well, this is the prediction of the vehicle. This is the actual vehicle. We plan that we should stop over here. The pedestrian has crossed. And then here, we understand that actually we can do the job even by left turning before the pedestrians come. And we do. This is Ivo. Now he's working at Zenseact and is, is basically performing this test. So, here we used the simulated pedestrian. We didn't have the permission to do test with human pedestrians, as you can imagine. Okay, we have improved this approach. Why? Because, as I said, the consistency requirement could be a little bit strict, could be a little bit stringent, overly conservative. So, Yin Shuai is a postdoc at Chalmers, working in a project together with Ericsson, where we are trying to collect information from cells, communication cells, to learn and then predict the behavior of humans in traffic. And what she has done here is to assume that for some reason the consistency assumption is broken. So what does it mean? It means that the inequality, which I showed you before, is also with some positive term over here. So recall that this should be negative, minus g is a positive quantity, so this stuff is a quantity over here, positive quantity over here. So it can be shown that actually, even in presence of bounded inconsistency assumption, so what you can do is to solve an extra step optimization, so an additional optimization problem that is basically telling you how much you should relax some constraints, for instance, on steering rate, braking rate, in order to cope with such inconsistency prediction. So what we do, the idea is the following. Well, if possible, we try to drive smoothly and gently and nicely. But if something happens, well, we are allowed to brake more than it would be necessary for a smooth and nice driving. So, for those of you who are interested in the technicalities, I can share some paper. But over here now, I want to show you some results based on real data that we got by using this that we call the uncertainty-aware MPC based motion planning. So what you are going to see here is a vehicle that is driving on a highway. It's real data collected on the ring around Gothenburg. And at some point, while traveling on our lane, there is a vehicle that is cutting basically our path to take an off-ramp. Okay, so what is going to happen is that the vehicle is driving with a comfort mode. Okay, very limited braking, very limited steering, to very limited jerk, lateral and longitudinal jerk, to plan very smooth path. But then at some point we see that this guy, so the guy cutting our path, is behaving in an inconsistent way. And then the question is, how much harder I should brake or steer to avoid the collision with this inconsistent guy? That's what you're going to see. So here is the data that is publicly available from this ZOD. It's called the Zenseact Open Dataset. It's very much similar to, for those of you who are familiar with Waymax, is the dataset released by Waymo. New Plan, which is the dataset released by, it will come. So what you see over here is that this vehicle is suddenly, yeah, that's what it's doing. Okay? So normally with the controller that we are using, we couldn't cope with such a cut and keep a safe distance. We recognize that we cannot. Then what we do is to switch to a controller which with different bounds such that the collision with this vehicle is guaranteed to not happen. So those are the results that you see over here. You see that the vehicle is braking as much as this, is allowed to brake as much as this, which I think is 3 meters per second square. But then at some point, we here we see this plot here shows the inconsistency of our prediction. So at some point, we detect that this vehicle that is overtaking on the left is moving suddenly to the right, so it's cutting our path. We recognize that our controller cannot do the job anymore. And what we do is to move to a different controller which is allowed to brake more. So in this way, we are allowed to avoid the collision with this vehicle. So in this version, we have just 3 different controllers. We have another version of this controller published in another conference. We don't know whether it's going to be accepted, where we basically have a continuum of controller. Okay, so we have found a way to solve the additional optimization problem very easily in time. Okay, so so far we have been talking about motion planning mostly in urban environment, and you have seen that the prediction, so the way we predict the behavior of the surrounding road users, play a central role. And you also have to modify the way you you solve your motion planning problem to cope for the uncertainty connected to the prediction of the surrounding road users. Now, at some point, what I was planning is to talk about how to make predictions of surrounding road users. But then I got, which is this part, which I can share, okay? But I will skip this part, because yesterday I got some slides from my student, who is, he has been part of the team of the Unimore racing, autonomous racing team. There are 2 competitions. One is called the India Autonomous Racing, that is done in US. Another one is called A2RL, which is done in Abu Dhabi. And this student has been in charge of designing the motion planning for autonomous racing. So yesterday he sent me some nice results. I thought it would have been more interesting and also more exciting to talk about the results. That's why I will skip this part. For those of you who are interested, I can share the slides, but also the papers, and jump to this. Okay, so that's what we are going to talk about. The results are, the PhD student I told you about is Francesco Prignoli. He's visiting Francesco Borrelli in UC Berkeley, my former PhD supervisor, and he got also some help from some local PhD student. So it's a joint work. Okay, so what we've been focusing on is the following. So in racing application, you have, when it comes to overtaking, you have a right-of-way rules, which is extremely important. I mean, if the defender does not respect this right-of-way rule, he gets penalties. Also in Formula 1, it's like that, right? So if you don't give enough way to, enough space, lateral space, to the attacker, when the attacker is close enough to the defender, you get a penalty. It can be a long lap penalty. Basically, you have to take a longer path, or you have to go through the pit lane. I mean, it's a punishment, right? Because you have broken a rule. So our question was, okay, if in the optimization problem we have seen before, also include those right-of-way rules, can we plan our path in order to be less conservative? Okay, can we take advantage of the knowledge of these right-of-way rules? So this is the question we are trying to answer. Why? Because in existing approach, what you do is the following. Well, there is another car you want to overtake. You know what is the best line, right? The shortest lap time path. You know that because it's depending on the track geometry. And what you do is to assume that the defender, the car you want to overtake, is just going to travel along that path at the maximum speed. Okay? So you completely disregard in some of the most common approach that this guy has to respect the right-of-way rule. Okay? Result, as you will see in a while, is that most of the time you abort the overtake. So you assume that this guy will leave you enough space to overtake, and you abort. There are approaches which instead also try to model the interaction between the defender and the attacker, but this is done only in terms of collision avoidance. So what you assume is that the defender, so the car you want to overtake, will only try to avoid the collision. But that's not the way it works in practice, right? Otherwise, you could just, point at the car, scare the car ahead, and here the driver will let you pass because, recognize that behind you have like a suicide path planner. And so what we've done instead is to code with a set of inequality, in the motion planner of the defender, the right-of-way rules, which basically says that when the distance, so the blue is the defender, so the car to be overtaken, the orange is the attacker, so the car that is overtaking. The rule is that when delta rho s, when the longitudinal distance is below a certain threshold, then the blue car should not decrease delta rho g, that is the lateral space. Okay? It should be from that point ahead, the lateral space left for the attacker should be larger or equal than delta rho g. That's the rule. It's one way of mathematically modeling the rule. So what we've done then is to model the defender as a vehicle that is planning its path with a model predictive controller, so exactly the way I've shown before, but we have coded the right-of-way rule. So we model the fact that the blue car is respecting the right-of-way rule. The orange car is planning the path consequently in a game theoretical scheme. It's a non-symmetric game because the blue car the only thing that the blue car does is trying to satisfy the right-of-way rule, while the collision avoidance is only in charge of the orange car. So it's an asymmetric game. Okay, so this is as I said, each car basically solve a very similar problem to what we saw at the beginning of the presentation. These two constraints are different for the orange and the blue car. For orange car, this one is a collision avoidance constraint, while for the blue car is right-of-way rules. So it's a set of constraints which impose the planned path of the defender to satisfy the right-of-way rules. The right-of-way rules can be written as a number of inequalities made of continuous variable and integer variable. That's why the problem you solve over here is a computationally nasty optimization problem. It's a nonlinear optimization problem with integer variable. Our goal is not at this stage to solve this problem in real time, is rather to answer the question, is really including the right-of-way rules paying off or not? Let's find it out. So here is, so far we just have simulations, so we don't have any on-field experiments. So what you are going to see are only simulations. So this is some simulation results, which shows you how the generalized Nash equilibrium problem, the generalized equilibrium, Nash equilibrium of this game theoretical problem is going to look like. So what happened is that, once more, this is the defender, this is the attacker. So here we have the attacker is close enough. So this means that this guy over here that is following this racing line in green should leave at least this distance from the left lane boundary. That's basically the right-of-way rule as we introduced before. So what happened is that here is the baseline controller. So you see in this pale blue, what we predict is that the defender will just keep following the racing line. Why? Because that's the most convenient thing to do, right? If you want to be fast, you just follow the racing line, which by definition is the minimum lap time racing line. Okay? So if this is the case, then the attacker tries to see if there exists any trajectory such that he can overtake the defender. That's not the case. So if the defender goes on the racing line, there is no way to overtake it. Aborted. So that's what happened instead by using our approach. So you see that the blue vehicle is following the racing line, but at some point it will see that the attacker has approached and it has to, the right-of-way rule must be satisfied. So it will deviate from the racing line, leaving enough space over here such that the attacker can overtake. So that's, I hope it's working. That's a simulation. So let me pause over here. So this is the baseline controller. Again, we just assume the defender is following the racing line without caring about the attacker, neither the attacker nor the right-of-way rule. Here, that's not the case. So what we are counting here are the overtakes compared to the number of possibility to overtakes. And since usually we overtakes in curves, in corners, that's basically the number of overtaking maneuvers over the number of overtaking possibilities of number of curves so far. So at this stage of the simulation, so with our approach, we have overtaken 6 out of 6 times. Clearly, sometimes we will also fail. In here, with the baseline approach, we have aborted all the times. So what you will see is that as the two vehicles travel along the track, those two numbers will increase. But clearly, not surprisingly, over here you will see that the success rate in our approach is much higher. So the yellow stripe is basically the space that the defender is supposed to leave according to the right-of-way rule. So on the left, you see that that space is not left. On the right, it is. And you see that over here, we have aborted all of the 18 or 23 now possibility to overtake that we had, while here we are at 22 over 23. Only once we had to abort. Well, it will go over and over again, and the outcome is that we succeeded in 93 out of 100 trials, while the baseline only makes 45 overtakes, successfully makes only 45 overtakings out of 100 possibilities, 100 corners. Okay. So I would close here my presentation. So most of the stuff that you have seen has been funded by the VASP, which is a research program in Sweden that stands for the Wallenberg Autonomous System Program. Wallenberg is a family, rich family in Sweden, funding this nice program since 2015. And is also partially funded by Vinnova, which is the innovation agency in Sweden, funding applied research together with companies. In this case, Zenseact, as I said, and Ericsson. And also some of the stuff that you've seen here has been funded by the Swedish Research Council. And yeah, those are the people I've been working with for in the project that you have just seen. Do I have more time, or? If you want, yeah. How much is, because I have changed my plans and...
We have never stopped people historically, so if you have something interesting to show you?
Yeah, I will be super fast just to give you a taste of what we've been doing when it comes to prediction. It's the part which I skipped to present this newer material that I received last night. Okay, so we are also working on the problem of how to make predictions, how to predict the behavior of humans in traffic. It can be highway traffic, it can be urban traffic. How is this done typically with nowadays with neural networks, of course. But what's the problem with neural networks? Well, the behavior, the prediction of how the traffic around us is going to behave, you have seen will going to end up in our optimization problem, right? And so basically the G function, the G inequality, G less equal than 0 inequality you have seen before. Well, the problem is that if you plug a neural network there, our problem is going to get quite nasty to solve. And just to give you a number, there is a famous paper out there, which is the kind of benchmark for predicting the behavior of road users, that is made of 500,000 parameters, a neural network with 500,000 parameters. Not really a nice object to have within an optimization problem. So that's why what we are doing is to try to solve this problem with prediction tools which have a more friendly mathematical structure. Let me show you what I mean by that. So we are using tools which have been used in opinion dynamics. Opinion dynamics are those mathematical tools describing, for instance, how preferences in networks develops depending on the influence with others. It can be Facebook, or it can be another social network, or it can be just a community. If we start a discussion over here, depending on the trust, we have the influence that we have between each of us, then some opinion will propagate in this community in different ways. So what we've done is try to explore if those tools can be useful to model the behavior in a traffic scenario. What in this type of tools, what you do is to model a single individual in a traffic scene as a Markov chain. And what you can do then is to form a network of Markov chains to also model the interaction between these Markov agents. Is that convenient? Well, yes, from one point of view. Why? Because if you describe with those pies the probabilities that an agent will make a decision rather than another one, then the evolution of these probabilities is described by this very nice system of linear differential equation, where you have some the elements which are on the main diagonal that describes what is called the isolated behaviors. So if I'm a pedestrian, I'm freely walking in the night in a city. There is no car or no other pedestrian around. What's the probability that I keep walking on the sidewalk rather than crossing the road? Well, it's basically just a statistical measure. I can just count the number of times a pedestrian at the time crosses or keep walking on the sidewalk. But then what happens is that you have also off-diagonal elements which describe the influences. So how likely is that I make this decision given that, for instance, Emanuele is making another decision? So if you properly define the decision space, that could be keep on walking on the sidewalk, crossing, or any other things. For a car, it could be go straight, turn right, turn left. Then you can describe to some extent the behavior of a traffic scene. What's the drawback? Well, the drawback is that the complexity of this, so the number of states in this mathematical model can very rapidly explode. So if the decision space is quite large, then this mathematical model can reach dozens of states very quickly. There are tricks you can place, marginalization or other things, but still, that can be a problem. So, what we are doing now is trying to calibrate these matrices over here. So this is the linear dynamical model that I tell you is going to describe the behavior of this network of Markovian agents. So those are, so one of these metrics describes what is called, again, the isolated behavior, but all these two matrices define the interactions, so attractive and repulsive force. In principle, there are tools out there to identify, to calibrate those matrices from experimental data, but that's actually what we are working on. So we are using some data from simulators to calibrate these matrices and be able to use these model structures in our motion planning, optimization-based motion planning algorithms, which we have seen before. So that's what we are doing on this side, on the prediction of road users' behavior. So I will stop here. I also have some additional work slides on this topic in case of some of you are interested, but yeah, I will stop here to be more concise. Thank you.
Okay, so thank you, Paolo, for your presentation. I imagine we have time for a few questions, so we start from the back.
I can shout out if you hear me.
No, but they will not hear you online.
Thanks, Paolo, for the nice talk. Every time I come at BrIAS, I remember why I choose biology. I know that 4 of you will be funny this one. I have 2 small questions. One stupid and one less stupid. You choose which one is it, the one.
Let's go for the stupid one.
No, you choose. Yeah. I give you the question. So first, you always like indicate the object in front of you, or like in the case of overtaking attacking a car that should leave you the space. But what about, considering the object behind the car?
That's not stupid at all, believe me. The project...
No, wait for the second question.
Okay, but then it's scary.
You choose.
This was the stupid one. Yeah.
The other one is like, I know, biology side. Have the community ever considered the fact of, sort of social behavior and cultural behavior when it comes to different parts of the world? I mean, like my mother always told me, like, if you are crossing the street, come back if there is a car approaching. My father say, no, keep running. And I don't know if, this is like Italian or European things, or you're in Sweden testing these things. The Swedish are maybe educated in a certain manner to keep straight walking. Or maybe if you go to Asia or if you go to South America, they might rather jump, or I don't know.
Yeah. Okay, let's start from the first. The first question is not trivial at all, actually. And with the Zense Act, the project we have right now, what we are doing is, so what we've seen is that in these data sets, so data from real world, okay, it's not fake artificial data. What we have seen is that some of the autonomous driving benchmark, they do really things which would annoy most of the drivers, like changing lane, okay, without recognizing that the car behind is coming at high speed, probably to overtake. And that could be very dangerous. You could also trigger an accident behind you, okay, just because we have not seen this. Don't consider extreme case like a collision, okay? It could be that you scare the driver that is coming from behind, and you trigger an accident 100 meters behind you. You are not involved, you have not collided, but still you are responsible for the accident. So what we are doing with Zense Act now is the following. It's still about prediction, because what we are trying to do is, if I plan this at time t+1, what the vehicles around me are going to do? Nothing special. Okay, let's keep planning. What if at time k+2 in the future, I do this? what the other vehicles are going to do. So it is called closed loop prediction. You can do it, so you can predict what to do, also based on the reaction that vehicles around you will have based on what you do. You can formulate such a problem rigorously, actually, as we have done also in the autonomous racing, but it's super complicated to solve. I mean, you need a supercomputer, and clearly it's paying off. We know that, okay? But then now the challenge is to do it fast enough to do it in real time. So yeah, the topic is I would say is one of the hottest topic in prediction in autonomous driving nowadays. And then when it comes to the second question, that is remind me. Sorry, I was. Yeah, right. Yeah, that's also a sensitive. I mean, a special problem because just to give an example, we were approached by an Indian company, and what they wanted to do is to make an adaptive cruise controller system for the Indian market. Okay, it's a simple system. It's a system that we have here since I would say late 90s. But none of the suppliers like Bosch, Continental, is going to deliver the product down there because the certification system is completely different. I mean, the traffic is so much different. And again, we are talking a super simple system, adaptive cruise control. You know what it is? I mean, it's keeping drive at some speed, and then it will slow down if there is a vehicle in front of you. Way, way simpler than autonomous driving and blah, blah, blah. Okay? But still, for that system, in the Indian market, they say no. So they will probably sell some license, but then the responsibility is from a local company. I'm not aware of any way of commercializing easily such a complex system in multiple markets, to be honest. I know that everyone is aware of the challenge, but to be honest, I'm not aware of any easy solution of this problem. Thank you.
Well, thanks for the nice talk, and sorry to make the classical question, but you showed before a mixed integer nonlinear programming problem. What's the average computational time for that?
I don't know. I mean, I didn't really. We didn't even write in the paper because again, it was not really the focus. But I guess I would say like probably even some dozens of seconds. Like it's a small problem, but quite many integer variables. So I would say it could be easily 20 seconds. Yeah. But again, I can double check. I can ask Francesco. I'll let you know if you're interested. Yeah.
Right. This was just for my curiosity to see what's the gap between the.
I would say it's a large gap.
Yeah.
Yeah.
So in your opinion, clearly this is not something we're gonna solve in the next 5 to 10 years using MI and OOP. What's a possible future approach?
A common approach when, for instance, we have used when we do like this uncertainty-aware controller when you have this unexpected behavior, and so we have to solve an additional problem. It's complicated, and what you can do is to approximate the solution of this problem with a neural network. And we have seen that when you solve the exact problem, the computational complexity can go up and down depending on how complicated is the traffic scene. When you use the neural network, the computational time is constant. It's pretty much constant. Clearly, if you have not trained well or with the right, whatever it means, data set, then the solution that you calculate with the neural network is going to be wrong. But that's one typical way of doing it. I don't know how easy it's going to be for this mixed integer problem, but this is probably something that we will try.
Thank you very much for a very nice talk that touched upon many different areas. Just to follow up a little bit on this idea of game theory and the generalized Nash equilibria, So there is also a cost function there.
Yes.
And one of the criticisms of game theoretic approach is that you need to know the cost of the opposing players. Is the cost kind of this attacking, defending framework is pretty well known or pretty well formulated?
I mean, right now, I mean, in this context, I would say it's easy to guess a cost because the defender will try to stay as close as possible to the racing line. But now one could think that the same idea could be applied also to a urban environment. And then what is the cost? That I don't know. I mean, it would be a little bit more difficult to guess because it would be like guessing, first of all, the reference path. Yeah, but then we are back to the previous problem. Is the car in front of us going straight, making a left turn or a right turn? So I would say that my answer would be, safe answer would be that in some cases it's easy to guess, in some other, no, not at all.
So, but it seems like this setting of racing is actually, you could probably argue that you might know the cost function of the opposing player better. How long is your kind of horizon, prediction horizon, in terms of seconds in this?
In terms of seconds, I think 1.5, if I'm not wrong.
1.5 seconds.
Yeah. At least this is what we started from, yes.
Thank you.
Okay, so I propose to thank again the speaker and